All right, session is now being recorded. Okay, so what I would like to do, what I offered to do here, the subject is sound this week. I have a couple of slides that go over some of the concepts in the chapter on sound, and then I've got some problems for you to try, and then we can go over them. I'm a little nervous about running out of time if I do the slides, because it's a fair number of slides, and we only have 40 minutes. What's your pleasure? Would you like me to do the slides, or do you want me to just jump into the problems so that you can give them a shot? What would be best for you guys, do you think?
I like going over the slides and then problems.
All right, so yeah, slides, please. All right, so slides, very good. Let's try the slides then. We'll share the screen. I'll try to. All right, here we go. Do you see the slides there?
Yes.
Okay, and Kelly, let me once again deputize you. Can you read whatever relevant questions show up, since I don't see them during presentation mode here?
Certainly.
Thank you. My pointer. Here we go. All right. What is sound? The answer is longitudinal pressure waves in air or other material. You can have sound in water, for example. But we'll think about air because that's how we experience sound mostly. And let me remind you what a longitudinal wave is. You can imagine taking a slinky, connecting one end to the wall, and then stretching it and moving your hand up and down like that, so you get this kind of a wave that you set up. That's transverse because the slinky material moves in a direction perpendicular to the direction of the waves. So if you make a pulse, the pulse moves to the, let's say, to the right, but the chunks of slinky move up and down instead, so perpendicular. A longitudinal wave, however, is like this. So you take the end of the slinky that's stretched and you move it back and forth. So you create these regions where the slinky is compressed and regions where it's expanded. And so the motion of the slinky is left and right, and the motion of the wave is also left and right. Well, in this case, to the right. Right, so the region of compression migrates to the right. So that's a longitudinal wave. So in air, you can only get longitudinal waves because when you compress something, the molecules push against each other and they try to expand. And if they're expanded, then there's some empty space and the molecules start to move into it. So you have this sort of effective restoring force. Whereas if you try to make a transverse wave, you just sort of move some air to the side or some water to the side, nothing particularly moves it back. So you get longitudinal waves in air or in water, but not transverse waves. Okay, so here's another more physical kind of depiction of what sound is. This thing over here, it kind of looks like a sideways drum. I guess it is a drum, and here's the membrane of the drum. It's moving back and forth. The membrane of a drum does very complicated motions. So let's imagine that this is just a simple speaker, and this is the surface of the speaker. And you run it with just a simple sine wave so that it just moves in and out without any complicated spatial movement, just in and out like that. And it does so, let's say, maybe 400 times per second. So it would be more or less 40, so that would be, A above middle C. As a result, the head of the membrane here compresses the air. As you see in this case, it's sort of moved out a little bit and compressed the air. And it did so a little bit earlier and created this region of compression, and before that created this one. And when the membrane moves to the left, it creates this sort of region where the pressure is lower, where there are fewer molecules. And so that's what a longitudinal pressure wave is. And I have this nice little animation here. I love this. This is really brilliant, I think. So here in gray is the surface of that speaker. Before it was sort of curved, but here we just have this wall that moves back and forth to make things simpler. And you see that it bunches up the molecules and then sort of sends them on their way, and it creates these waves of the molecules. As it moves to the left, it kind of it looks like it kind of pulls them to the left, but it doesn't really do that. It just moves out of the way, and then the molecules diffuse into there. And so you see, it kind of looks like it's pushing a bunch of molecules, and then they just kind of move to the right. But it's not quite that. If you pay attention to the little red molecule here, you'll see, and actually the next slide will have a little arrow on it. You see the molecule just moves left and right and doesn't, on average, go anywhere. It just moves a little bit to the right and then back to the left. And the one over here does the same thing. The one over here does the same thing. Here's one down here. Whereas the wave, you see that the wave propagates all the way along. So just like on a string, a transverse wave on a string, the chunk of string moves up and down, and then the wave is the signal that gets propagated. The actual string doesn't propagate down, it just goes up and down. Similarly here, the molecules in a pressure wave don't move along with the wave, they just move back and forth. All right, so that's what sound is, basically. This is in 1 dimension, so you can imagine this also happens in 3 dimensions. Here is a depiction of a sort of snapshot in time of the picture I just showed you, where you see the density of air is higher here and lower here and higher here. So you could graph what the density is, and you get something like this versus space. Here's the x-coordinate, high density, low density. And so you could depict the sound wave like this. And so you would have an amplitude where the density is, the change in density from normal to its maximum up here. So there's the amplitude, or the amplitude the other way. You also have a wavelength, the distance between, say, this point and that point, or the distance between that point and that point. A wavelength. You also have a frequency, because as you saw, these regions of dense air move to the right. So how many waves per unit time, that would give you the period, and inverse of that is a frequency. Actually, I have this in the next slide, I forgot. All right, so here's the standard wave. It could be anything. It could be the picture that I just showed you of density versus space. And so you have the typical wave characteristics, amplitude and wavelength and frequency and period, and then the wave velocity v. All right, so all these things can be defined for sound waves as well. And remember this formulation, that the speed of the wave is the wavelength times the frequency. And that's true for any wave. So that's a good thing to remember. Speed of the wave is the wavelength times the frequency. Okay, so again, I can't give you, excuse me, full-blown discussion of everything in this chapter because we only have 1 session. So I'm just going to pick some of the topics which I've seen students have some difficulty with over the years. I can't do all of them. And one of them is this, the vibrating columns of air in tubes. So let's consider a tube that's open at both ends. And what we're doing is we're setting up standing waves. We just talked about a wave, pressure wave in air. And so a standing wave is one where the wave goes down and then sort of reflects, and you get a pattern that sort of stays stationary in space. You can do that with rope on a string. Right? Remember, you could tie the string to one end, to the wall over here, and then with your hand sort of flick, and you get a pulse. The pulse will hit this end over here and reflect. And if you time things perfectly, then you can set up this kind of a standing wave. So in this case, the rope is up here, a moment later it's down here, and then a moment later it's up there again, and you get this pattern, which doesn't move spatially. If you move your hand twice as fast, as it were, you could set up this kind of a pattern, where the rope looks like this, up and down, and a moment later it'll be reversed, down and up, and it'll oscillate back and forth like that. And if you are able to move your hand even faster, you can set this up. And that's a little bit harder to do, but you can do that. So that's what standing waves are. And you can do that with pressure waves in a tube. So let's consider a tube that's open at both ends. And this diagram is what sometimes confuses a lot of people. I remember when I was studying this the very first time, I was perplexed by the meaning of this diagram. It's very strange, I have to say. But all right, we have a tube. So imagine that it's a cross-sectional, a tube whose cross-section is circular. And what we've arranged it so that The length of the tube is in the plane of the screen, and we're slicing it right down the middle. So half of the tube is behind the screen and half of the tube is in front of the screen, and it intersects the screen at these blue lines here, so that the circular cross-section is perpendicular to the screen. Right, we're just looking right down the middle of the tube. And then there are these mysterious lines, which here there's one that's magenta and one that's kind of, I'm going to call it orange. It's kind of reddish orange. Let me just call it orange. Orange and magenta. Every physics book I've seen, when they discuss this phenomenon of standing waves of air in tubes, makes a diagram like that. And what the heck do these things mean? Well, down here is the physical manifestation of what's actually happening. The molecules in the air move back and forth when you have one of these standing waves going on. So in particular, at this end of the tube, you've got some molecules that move back and forth and back and forth and back and forth. So in and out of the tube on this end. Same thing over here. They go in and out. And in the middle, they don't do anything. They're just, they're stuck. So the meaning of this magenta and orange thing is, let's say when the magenta line is up here, it means that this molecule is all the way to the left. And as it comes back into the tube, this magenta line is supposed to come down and then be over here. And when it's the orange line, then the molecule is all the way to the right. So similar to the diagram of the rope that I just showed you, where it depicts the shape of the rope at one moment and then the next moment and then the next moment. These lines are supposed to depict the position of this molecule here being, say, all the way to the left when it's red up here, and then it comes down, and when the molecule is all the way to the right, then this red line would have moved down to where this orange line is at the moment. So it's showing you the two extremes. In the middle, you see that they coincide, and so the extremes of the motion of that molecule are the same point in space, so that molecule doesn't go anywhere. And then let me also indicate that, point out to you that you have the magenta line up here, and on the other end, you've got the orange line up here. So what that means is that in this snapshot, this molecule is all the way to the left, and at the same time, this molecule is all the way to the right. So this one moves to the right, that one moves to the left, and then when this one has moved into the tube, this one is also moving into the tube. So in that sense, the motion of this molecule at this end and the motion of that molecule on this end is out of phase, right? They both move out of the tube and into the tube at the same time. Is that sufficiently clear? I hope that's clear. Can I get
so?
Go ahead.
All is quiet on the Western Front, so I'm going to go with a yes.
Okay. Yeah. Let me get some feedback from people. Can you type into the chat? Does this make sense? Do you understand these diagrams?
Everyone said.
And Kelly, can you translate for me?
Yep, they all say yes.
Dr. Barrett,
Okay.
so you're saying
Yes, go ahead.
the magenta line is on the left side is going to come back down to the orange vertically down as like a standing wave. Is that what you were saying earlier?
Yeah.
Okay.
So if I could make an animation, this magenta line would be like this at one moment, and then it would be flat, and it would be in the position of the orange line, and then it would be flat, and then it would come back to where it is then. You can imagine it would sort of fluctuate up and down like that. Does that make sense?
Mm-hmm. Okay.
And what
Yes,
that means
thank you.
physically is that the molecules are actually moving back and forth, the way they're depicted here. Okay, so let's discuss what kinds of standing waves we can set up in a tube like this. So here I've told you something. So these curves represent the displacement of molecules at times half a period apart. Right, one entire period is when the molecule moves out, in, and then back out again. There's the actual motion of the molecules. The node is where the molecules don't move, and the open ends are called antinodes. So the air can move in and out where the antinodes are. The fundamental mode has one node in the middle. So that's the simplest kind of a standing wave is this geometry, where there's one node in the middle. So let's consider that one. That's the fundamental called the fundamental. The mode of oscillation is called the fundamental, first harmonic. And so the question is, what is the wavelength? And let me go back to the previous slide. So as I indicated, since this is magenta up here and that's orange up here, what that means is that when this molecule is moving out, that molecule is moving out as well. So if you want to talk about wavelength, you need to find where the molecules are moving synchronously. So if you were to copy the tube over again like this, and sort of reverse it, so that you have this pattern, you see this orange line goes all the way up here like that. What that would mean is that you'd have a molecule here, see the magenta, let's see the magenta. That means the molecule is moving out over here to the left. And over here, that molecule on this end is also moving to the left. So in this longer tube, the motion of the molecules here is exactly synchronized with the motions of the molecules over here. When this one moves to the left, that one moves to the left. And since the magenta line is down here, the molecules here are moving to the right. So that's why we have one full wavelength being this long. It's the distance between molecules that are doing the same thing simultaneously, synchronously. And so you see, what I had to do in order to depict one entire wavelength is double the length of the tube. So the wavelength of this fundamental mode of oscillation is twice the length of the pipe. All right? Okay, so we can do something with this now that we've identified the wavelength of this fundamental oscillation. Here's this relationship that I told you. The speed of waves is the wavelength times the frequency. Solve the frequency, and it's v over lambda. And we know the wavelength over here, so let's plug that wavelength into this formula for the frequency. We have the speed of waves, divided by 2 times L. So the v is the speed of sound. And so now we know what the frequency, if we know what the speed of sound is and the length of the pipe, we know the frequency of this fundamental mode of oscillation. So we can write that as F1. Let me point out then, so in the actual pipe of length L, we get half of a wavelength. It's just the same as my string. When I had the fundamental oscillation, there's 1/2 of wavelength. Right? A full wavelength would be all the way over here like this. In this case, we see we have one entire wavelength. Here's half a wavelength. Just like that, we have the same thing in the first oscillation here. Wavelength inside the tube. The next thing you could do, just like on the string, is set it up so that you've got 2 nodes inside this open tube. So here the molecules are moving in and out. Here they're stationary. Here they're moving in and out anti-synchronously to the ones out here. Here they're stationary. And then here this one is synchronized with the molecules over there. When this molecule moves out, this molecule moves to the left, moves in. Right, so these molecules are synchronized with those. And you can see that you have one entire wavelength inside of the tube. So the wavelength is just equal to the length of the tube. So again, using this formula here, frequency is the speed of sound divided by the wavelength. Plug the wavelength in, and we get the frequency is v over L. Notice that that's twice as much as the fundamental frequency. So I could write that as 2 times this. So the first overtone, or the second harmonic, has a frequency which is twice as much. Here's the next situation where you've got 3 nodes, right? 1 node, 2 nodes, and now 3 nodes. And this one's a little more complicated, just looking at the diagram to figure out what the wavelength is. So here I have a copy of that same tube. If you divide it up into thirds like this, you can see you have one full wavelength in 2 of those thirds. So the wavelength is from there to there, and that's 2/3 of the length of the pipe. So again, plug that into frequency as the speed over the wavelength, and we get this. Denominator is the numerator, so the 3 is up here. And notice that we can factor out the V over 2L, which is what the fundamental frequency is. And we just write it in terms of F1 as 3 times that. So we get this relationship. So you can see the pattern, right? The first mode of oscillation is F1, V over 2L. The second one is twice as much. The third one is 3 times as much. So in general, you have this relationship here. The frequency of the nth mode of oscillation, the nth harmonic, is an integer times the fundamental frequency, where the integer n is 1, 2, 3, 4, 5, etc. Okay?
Yep.
That's clear?
Yep.
Say again, Kelly?
We're good.
We're good. All right, very good.
Dr. Beretta,
Yes, go ahead.
can you explain the pattern with the overtones we see here?
Explain the what with the overtones?
Overtone, the first overtone and the second overtone, is that also
What the words mean?
Mm-hmm.
So the terminology is confusing. So harmonics are this. So there's a fundamental mode of oscillation, and that has a certain frequency. A harmonic is an integer number times that frequency. So a mode of oscillation that has an integer number just like this. So that's the first harmonic, second harmonic, third harmonic. So harmonics are just integer times the fundamental frequency. Overtones are what happens when you add another node in between. So you have got the fundamental, and then the first overtone is the next one after that, the second overtone, the next one after that. So it's just strange terminology. You'll see in the next couple of slides a little bit more about how these are different, harmonics and overtones. So let me come back to your question after I've reviewed the next one.
She said, great, thank you.
Okay. All right, so let's consider now for a moment the vibrating column of air in a tube that's closed at one end. So you see it's closed over here. And the presence of the tube wall here means that the molecules on this end can't move because there's a wall there. So the most basic kind of a standing wave that you can have is the molecules move in and out on this end, but they don't move on that end. And so that's why you've got the magenta line up here and the orange line down here. They coincide here, meaning the molecules don't move. And they're different here, meaning the molecules move in and out. So that's the fundamental mode of oscillation. So the first harmonic is that. And without going into the geometric construction, you can work out that the wavelength of this is actually 4 times the length. You only see 1/4 of a wave. You can imagine extending it so it goes here and then down and then up again to make the entire wavelength. So plugging it in again into frequency is speed of wave over the wavelength. Plug in the wavelength is 4L, you get this frequency for the fundamental oscillation. It's the speed of sound divided by 4 times the length of the pipe. Here are the next modes of oscillation that you can get. So there's one node here, and then you get next one has 2 nodes, you see. And so that's the first overtone. Add another node and you get the second overtone. But what's interesting is that if you work out these frequencies, notice that you've got the fundamental frequency, and then the next one, the next mode of oscillation, is 3 times the fundamental frequency. It's not 2 times like it was for the tube open at both ends. It's 3. That's why this is called the third harmonic, because it's 3 times the fundamental frequency. 2 times the fundamental frequency is not a possible mode of oscillation if the tube is closed at one end. And the next one, where you've got 1, 2, 3 nodes, would then be the second overtone, because it's the second thing that you could have over the first one. Its frequency is 5 times the fundamental frequency, so it's the 5th harmonic. And so harmonics are given by an integer number of the fundamental frequencies, but the overtones are, this just tells you the sequence of the possible standing waves that you can have in the case. So that's why this terminology is different, and it can be confusing. Okay, but you only get the odd harmonics when you have a tube that's closed at one end. See, fundamental, and then 3, and then 5, and then principal, you can keep going higher. So the formula for the tube closed at one end is this one. The nth frequency, there's something in the way and I can't see what that says. Actually, I can go to the next slide. Here we go. This is supposed to be an M. Sorry about that. So with a tube open at both ends, you get all the harmonics, meaning any integer times the frequency, the fundamental frequency. But if it's closed at one end, you only get the odd harmonics, an odd number times the fundamental frequencies. Okay. All right. So
We're good.
Yeah, we're good. All right. So I'll go on because of time. Briefly, let's talk about beats. So you can imagine that there could be two sources of sound. And in 3 dimensions, the sound waves would come out like this. The blue lines here indicate, say, the regions of maximum compression of the air, let's say. And so these speakers put out the sound waves, and so you see that. And they overlap. So the dark blue ones come from B, the light blue ones come from A. And so as a result, these waves will interfere with each other. If we look at C, at point C, distance, the location that's equidistant from both speakers, and if we further assume that the speakers are moving identically, the same frequency and in the same, when A is out, B is out, etc. Then when you look at C, the sound waves that arrive there are synchronized with the sound waves that arrive from B, and so we have constructive interference at that location. In other words, we have maximum compression coming from A, you also have the maximum compression coming from B, and so you get twice as much of maximum compression at that moment. Constructive interference at C. But what happens if the frequency from the two speakers are a little bit different? So what if two sound waves of slightly different frequency mix together at that point? Two sound waves are coming at to the same location in space, but have slightly different frequencies. And so you get something like this. And I'm also assuming that the amplitudes of the waves are identical, as you can see here. But we have in this case, the light blue one is a frequency of 60 hertz, and the red one is 50 hertz. So what happens is at time 0, let's say that we have the maximum compression of the air from both waves. And so they add together and you get a lot of compression. But 0.05 seconds later, at this moment in time, we've got the maximum compression from one wave and the maximum expansion of the air simultaneously arriving at that point in space. So they'll cancel each other out. The result is that you end up with a pressure profile like this in time. The x-axis is in time. Maximum compression at time equals 0. A little bit later, at this point here, nothing happens because the waves cancel each other. But then they shift through each other again, and we return to maximum compression from both. Add these two together, and you get this. And so you see that it's loud for a moment, and then silent, and then loud, and then silent. You get this sort of wah, 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 wah effect. And the period, as depicted here, of the beats. The beats is the envelope of this added symbol. In this case, is 0.1 seconds. In terms of frequency, the beat frequency, which is the frequency of this thing, the wah wah wahs that you see here, is the difference in the frequency of the two waves. It's a nice simple relationship. The difference is 10 hertz. So a 10 hertz frequency for that corresponds to 1 over 10 hertz is 0.1 seconds, period of 0.1 seconds. Did you guys see a demonstration of a video of this with the tuning forks, and you see the
Yeah,
that
actually, that was the video.
Okay, good. Yeah, that's sort of standard. So, all right. Again, I'm low on time, so I'll continue. Doppler effect. A little bit of discussion of the Doppler effect. Doppler effect occurs when a source of sound moves with respect to an observer. So we're all familiar with this. When a fire truck drives by, we hear a change in the pitch, right? Suppose that there's a fire truck at rest and it's got a siren. And let's assume that the siren is just a simple tone rather than a. Let's say it's just going to go ah at a certain frequency. So the sound waves look, not complicated. They look like this. Here's somebody at rest over here. Here's another person at rest over there. And they hear these sound waves. They propagate out from the fire truck and hit their ears, and so they hear something. If everything is at rest, fire truck's at rest, the observer's at rest, and the other observer's at rest, they detect the same frequency. They hear the same pitch coming from the fire truck. But if the fire truck moves, in this case to the right, well, a sound wave gets put out, right, a maximum compression, say, and then the fire truck moves before maximally compressing the air again. So the sound waves get bunched together. So this person over here will detect a higher frequency because more of these blue lines hit her per unit time, looks like a her. And so there's a higher frequency and shorter wavelength. In contrast, this person over here receives one sound wave, but then the source has moved away before the next sound wave is put out. And so he detects a lower frequency. It'll be a lower pitch for him and a higher pitch for her. Same thing happens if the truck is at rest and the person moves. So it's hard to draw that picture, but you can imagine if this person runs towards the truck, she will encounter more of these blue lines indicating the maximum compression per unit time than if she were just standing still. She would measure a higher frequency. The person encounters more wavefronts per second when moving towards a truck than when standing still. And if this guy moves away from the truck, then that person would encounter fewer wavefronts per second, and so would measure a lower frequency. So you could get the same effect if the truck moves or if the person moves. And for that matter, if the person and the truck move, you can also get the same effect. So that's why this happens intuitively. You can do an analysis and you come up with the following formula. So to write down the formula, first let me indicate F. F is the frequency of the sound emitted by the source as measured when the source and the observer are stationary. So in the picture before, the two people are standing still, the truck is standing still. F is the frequency of the sound that the observers measure. Now let's assume that the sound source and or the observer move. And let's let F prime be the frequency that's measured by the observer. The sound will be the speed of sound. Here's the formula that you want that tells you what the Doppler effect is. The frequency measured by the observer, the F prime, is this ugly formula, this factor, times the frequency of the source when nothing is moving. So there's V sound, and here's V sound. Here's the speed of the observer, and here's the speed of the source. Now, the signs here, notice that there's a plus and a minus and a minus and a plus. You use the upper signs if the source and observer end up moving closer together. So if let's say the fire truck is moving to the right, then that means he's moving to the person on the right. You would use the upper signs. Or if the person on the right is moving towards the fire truck, you would also move them just because the source and the observer move closer together. If they end up moving apart either way, then you use the lower signs. Okay, so this is a nice compact way of writing down the formula. Just make sure you understand when you use the upper and the lower signs and what all these symbols mean. All right, moving on. Again, I'm running out of time. Sound level. This is a little bit strange. So loudness is a sensation. How loud a sound seems to be is a sensation. It is related to the intensity of a sound wave in a complicated way. So the first thing to talk about is just the physical meaning of a sound wave. So the intensity, not the perception of it, but just the intensity. Intensity is how much energy is delivered by the sound wave per unit time per unit area. Right, so if you've got a window and you turn on the music in the house, the speaker that's playing the music delivers a certain amount of energy per unit time to the window, but it also depends on the size of the window. So intensity then is measured, as you can see, in watts per meter squared. Energy divided by time is watts, joules per second, and area is meters per second, meter squared. Okay, so that's the physical reality of a sound wave. It can deliver this much energy per unit time per unit area, and so it has a certain intensity. Sound level, in other words, the number of decibels, is a way of writing down what the intensity is. It's mathematically identical or related to them. But loudness, meaning the sensation of how loud something is something that's different. In fons. I don't know if you are discussing this in class or not. But let's put that off for the moment and just talk about what decibels are. So sound level beta in decibels is this formula. 10 times the base 10 log of this ratio of intensities, where this I sub 0 is a reference intensity, usually taken to be the threshold of hearing, which is 10 to the minus 12 watts per square meter. So the sound level is dimensionless. It just tells you what the intensity of sound wave is relative to this reference through this formula. You can invert the formula, just mathematically manipulate it, and you can get the intensity in terms of the number of decibels. Plug in the number of decibels beta here, and multiply all this out, and you get the intensity of the wave. Okay, I think, oh yeah, and so the important thing to remember when you use this formula is when you're mixing sounds. So suppose you're standing there listening to a trumpet player. You could measure the number of decibels, or you could express it in terms of the intensity that you're receiving of sound. And now if you've got another sound source, say another trumpet player, and you want what the sound level is, you don't add the number of decibels. Instead, what you do is you figure out what the intensity is. You add the intensities, right? Because each trumpet player is delivering a certain number of joules per second, excuse me, joules per square meter to your ear. And so if you add another one, then you're adding more joules per square meter to your ear. So it's appropriate to add the intensity. Don't add the decibels, right? Because you've got this logarithm in there, you can't add the decibels. So if you want to know what the sound level is when you're mixing sounds, convert everything to intensities, figure out what the intensity is when everything is added together, and then convert back to decibels. Is that clear? Any question about that?
No, it appears to be clear.
All right. All right, so that's it. That's what I wanted to say. I've got a couple of other slides in there about fonts, but I'm going to leave that out. I'll include it when I post it. But we've got a little bit of time for some practice problems. Let me try to figure out how to show that to you. Share file. Here we go. Uploading. Stay with me. There. Can you see 7 problems there?
Yes.
Okay, very good. Now remember, you've got this little tool at the left so that you can zoom in. I'm doing it now, but I think you don't see it, but you can use that to zoom in and you can scroll through and look at these problems. So take a few minutes and try out these problems. Let me recommend that you skip number 5 for now because it involves a little bit more math than the others, and in the interest of time, try doing these. Skip number 5 for now. I'll post a solution eventually. And while you're doing that, I'm going to record attendance. I couldn't figure out a way to get it out of the recording, so I'm going to go old school again. I have my little sheet here. I'm going to look at the participant list and just check you off. All right, so give those problems a try while I do this. Is Victor Lopez here? Or Annie Nguyen? Or Will Rastatter? Or Michelle Trong? Or Jamili Wiggins? Okay. Everybody else I have recorded. Yoder, I have you recorded. What was your last name before? Aha, gotcha. All right, thank you for telling me, because it was mysterious. Couldn't figure out what had happened there. Okay, so we've got maybe 7 or so minutes. Shall we go over this?
Yes.
Let me set up my my thing here so I can. All righty. All right. Some of these are easy, some are a little bit more involved. Number one, the lowest tone to resonate in a pipe of length L is one that is open at both ends. So that's just like the example that I went over. Lowest tone is 200 hertz. Which one of the following frequencies will not resonate? Well, remember that the pipe is open at both ends. We get all the integer multiples of the fundamental frequency. So if we look at what's listed there, 200, well, we definitely get that because it says so. 400 is 2 times that. 600 is 3 times that, et cetera, 800. So 900 is not a multiple of 200 hertz. So that one is the one that will not happen. Yes, correct, E. Okay, does that make sense? 900 is just not an integer number times 200. All righty. Number two, 2 strings both vibrate at exactly 819 hertz. The tension in one of them is then increased slightly. As a result, 6 beats per second are heard when both strings vibrate. So what is the new frequency of the string that was tightened? So the beat frequency, so frequency beat, will be the absolute value of the difference. In this case, we have a higher frequency. So we have 819 plus question mark minus 819. Right? That's the difference of the higher frequency. The frequency of the string that's been tightened is this, and this is the other one. And when they play at the same time, you get the difference, as I've written here. So the beat frequency, and that would tell us that is 6. So question mark equals 6. So therefore, the frequency of the higher one is 819 plus 6. So 819 plus 6 is 825. So yeah. Is that clear? 825. Okay, very good. What is the intensity level in decibels of a sound with intensity 10 to the minus 3 watts per square meter? Let's just plug into the formula. So, unfortunately, I don't have much space here. I think what I can do is come down here. I'm going to write below number 7 if you can scroll down. So beta, just plug into the number here, 10 log base 10 of 10 to the minus 3 divided by 10 to the minus 12. Right, because the sound intensity that's given is 10 to the minus 3. All right, so now you don't need a calculator for this, right? It's 10 times the log of 10 to the 12 minus 3. Right? Just treating these exponents, right? And the log base 10 of 10 to the 9 is 9. So 10 times 9 is 90 decibels. So yes, correct 90 decibels, as you can see here. 90 decibels. Okay? All right, let's do number 4 here. 2 police cars have identical sirens that produce sound frequency of 570 hertz. The stationary listener is standing between the 2 cars. One car is parked, and the other is approaching. All right, so we've got 2 sounds mixing, so we're going to get a beat frequency, but then one is moving, so we've got the Doppler effect going on. Both cars parked and the other is approaching the listener, and both have the sirens on. The listener measured 9 beats per second. So that means is that we have the parked car delivering a sound of 570 hertz, and the listener hears the moving car sounding at 579 hertz. So find the speed of the approaching police car. All right, so we've got frequency is 570 hertz. The perceived frequency of the one that's moving is 579. And we know that because when these 2 sounds mix, we get beat frequency of 9 hertz, the difference between these 2 numbers. All right, what is the speed of the car? So let's put this into the formula for the Doppler effect. And now, are these guys moving towards each other, or are they moving apart from each other? One car is parked and the other is approaching the listener. So they're moving together. So that means you use the upper signs in that formula. And it looks like this. So V sound. Yeah, upper, exactly. V sound. And we've got a plus and a minus. Up here we have the sound of, the speed of the observer. The way the problem is worded, the observer is not moving, so we put a 0 here. And down here we've got the speed of the source. Okay, so there's the Doppler formula set up for this problem. Do the algebra and solve for V source. I don't have the time to do it. I'm just going to write down what the answer is. V source equals F prime minus F divided by F prime times the Vs. That's the speed of sound. And when you plug in numbers, you're going to get 5.28 meters per second. Okay, so that's the formula set up for this problem. I'm leaving out the algebra because I don't have time. But if you solve for V source, you'll get this. Plug in the numbers, they give you the speed of sound, and you get 5.28 meters per second. Right, they tell you speed of sound is 340 meters per second. Okay, I'm out of time, but before you go, let me ask you, was this helpful? Was it useful to go over all of those slides, or would it be helpful if I spend more time doing these problems? Okay, very good. All right, I'm going to post all the slides, and I'm going to post these problems with their solutions. My handwriting is sloppy, so I might have to rewrite them a little bit. Yeah, so you'll have the problems, Jackie. I'm going to post them, and so you can try them and have the solutions with them too. Okay, very good. Keep me posted as to what is useful and what is not useful, because I want this time to be helpful for you guys. But time is up, so have a good week. See you next time. Bye, guys.
Dr. Brito, I was wondering, could you explain again how you got the 579 hertz from the beat frequency?
Do you see at the bottom of the screen here?
Mm-hmm.
All right, so let me draw this line here to separate. Put my finger up here. Okay, so the police car that's not moving is delivering to the observer a sound that has frequency 570 hertz. It's hard to read, but that says 570.
Okay.
Right?
Mhm.
And then the observer also receives sound from the moving car. Those sounds mix, and the observer hears a beat frequency of 9 hertz. That's given a problem. So from that, we can conclude that the frequency of the other sound is 579 hertz. It could be 570 minus 9 hertz,
Yeah,
but we know that's not the case because the car is moving towards the listener.
towards the list.
So the listener will hear a higher pitch.
The listener. Okay. No,
Does that make sense?
that's great. Thank you for clarifying that.
Okay, so then the listener is receiving 570 hertz from the not moving car. So that's what the frequency is here, because both of the cars have the same siren. And then the frequency that is received by the observer from the moving car is measured at 579 hertz. So that's the F prime on this side of the formula. So in between, we've got to look at the formula and see what is there. Here's the speed of sound and speed of sound. Since the source and the observer are moving towards each other, we use the upper signs, so plus in the numerator, 0 in the denominator. And what would go here is the speed of the observer. Problem says the observer is just standing there, so put a 0 there. And then here's the speed of the source, the car, the speed of the car moving towards the observer. So having set up the Doppler formula like this, we can then solve for V source. So if you just do that algebra, then you'll get this result. And then plug in the numbers, right? F prime is 579, F is 570, and speed of sound is 340, I think is what the problem tells you. Yeah, 340 per second. Works out to 5.28 meters per second.
That's perfect. Thank you for re-explaining that, Dr. Barreto.
Sure, no problem.
So the sign, if it were the signs at the bottom, then you would use the minus in the numerator and the positive in the
Well, that's if the source were moving away,
away.
or I should say, the source and the observer were moving away from each other.
Away from each other. Okay. Okay.
That can happen if the observer is stationary and the car moves away, or if the car is stationary and the observer moves away. Then you would have a minus sign in the numerator and a plus sign in the denominator.
Okay. That's great. Thank you so much.
Sure, no problem.
Enjoy the rest of your day. Take care.
You too.
Thank you.
All right, I'm going to stop the recording now. Bye, everybody.